Okay, so I just wanted to talk to you about the little quiz for a minute. I don't know why in my mind, I just thought I was doing it the same way as last semester, but apparently I'm not, and it's confusing to people. But basically, the quizzes are in my office. You can pick up a quiz in my office anytime you walk by. There's a sign-out sheet. It's the same way we administered the exams in the library. Basically, you pick up the quiz, you take it home. Okay, when you open it, you're committed to it. It's 1 hour long, and it's due on Monday. It's not immensely long, so I'm assuming an hour will be more than enough time, okay? They're very low-level packaging in that I didn't put periodic tables or anything like that on them, okay? So if you need those, you have to dig them up yourself. But it is a closed book test. Closed notes, you're not allowed to discuss it. You're supposed to do it by yourself, okay? So I want to make sure that's clear. They're in my office, and then over the weekend, I'm going to put the exams in the library, all right? I said I'd give a brief review on this, and it's going to be a very brief review because we just did this in class. And what it's on, as I told you, is it's on fragmentation of aromatic compounds, okay? And it's on thermodynamics, the thermodynamic reaction, Friedel-Crafts reaction. So, in terms of GCMS, okay, the main thing, and I hate to keep repeating this because it's very repetitive, but for example, you should be able to deal with the fact that if you had an aromatic like this, you know, we did some like this in, let's say you had something like that, and this thing was hit with the electron beam, all right? This is in the mass spectrometer. That's the main thing I want you to focus on, not the GC aspect of it, because we've done that in lab. This would, in all likelihood, form some kind of, maybe we'll make this a little fancier like that. This would, in all likelihood, form some sort of radical cation. That's not the only thing you can do, but that's probably pretty likely. And as we said in class, most likely event is the ejection of a pi electron, okay, to make this kind of species, which is called a radical cation. This type of species is responsible for what we would call the molecular ion, which represents the molecular weight of the compound. So you would have to be able to, calculate the molecular weight, so maybe you need a periodic table of that, and know where it would occur in a spectrum, okay? This undergoes fragmentation. One type of fragmentation that it could undergo is it could lose an ethyl group either from here or here, in which case I would get this kind of intermediate. With the loss of this radical, that's an ethyl radical, that's a loss of 29. So whatever this molecular weight is, I'm not going to waste time on the video calculating the molecular weight of this, or maybe I can really quick. 6, 7, 8, 9, 10, 11, 12, so that's 144. And then 1, 2, 3, that's 36, so that's 180. And this is C, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is C15H32, and it's got an unsaturation number 4, roughly. So it's H36. What did I just say, 32? No, it's not H36, it's H34. So I got to add 34 into this. So I believe the molecular weight of this is 2... Remember us doing this in class, huh? 214, okay? So the molecular ion for this would be at 214. This is a loss of 29. So to get the mass of this, you'd take 214 minus 29, right? So that would get you to 180 plus, so it'd be like 185, I believe, okay? So you should see a big peak at 185. If I make math mistakes, tell me, okay? Am I okay so far? You think my math is okay?
Yeah, I think it's fair.
All right, good.
Try it.
That's something I would accept corrections on.
So I'm an accountant, I don't do math.
Yeah, right. Well, okay. So anyway, from this you would get a tropylium ion. It involves a rearrangement. You don't have to know how to do that, but you would get a tropylium ion, and this tropylium ion would also have 185, okay, as its molecular weight. Another thing this could do right, is this could slice the other way, like that. And we did this in class, so I mean, I'm assuming people took notes. We did a couple examples like this. So this would give you this, like that. And this has, this is a loss of 4, so I expect you guys to work that out. Okay, so you'd lose that piece off of it. This would become a tropylamine that would look roughly like this. Remember, tropylamines are aromatic, and we went over multiple times why they're aromatic, and you did in class multiple times. Okay, this would have same molecular ion, obviously, loss of 4, so this would be 48 plus however many hydrogens it has, which is 3, 4, 5, 6, 7, 8, 9. So this is 57, which is actually kind of a famous mass loss. So if this were happening, you would expect 214 minus 57, okay? And that is 157, I believe, right? So that's 157. So this you would see a big peak at the mass. It's called charge to mass. Mass to charge, rather, at 157. Now the question is, which of these would dominate? We talked about this in class, so you could spit out that radical or this radical. This radical is a little more stable, so my prediction is that probably this 157 peak would be one of the major peaks in the spectrum. Okay? The other thing you need to know how to do, and I don't know how much of this I'm going to do here, because I feel like we did it in gory detail in class, but you know, we talked in class about how you would go from, you know, like it could be anything, but let's say, how would I go from here, I don't know, we were doing something different. So we had like this, and we talked in class about how we would go from this, thinking about it as an equilibrium with AlCl3 and HCl or HBr, how we would go from here to here. Like that, okay? And what this entails is going backwards, okay? Or at least this is one way to explain it. I've seen other explanations of it. But if you're truly viewing it as an equilibrium and that the reaction is an equilibrium, you might want to consider the reaction going backwards. And of course, in reverse, you would simply protonate the carbon that you want to move. And I think you guys should rethink this and think this out a little bit. Now again, this is a thermodynamic reaction. So you would get this like that. Okay, then what would happen? Well, the bromide's been kicked out. And one of the reasons I'm doing this is I felt, you know, people did this and we did it kind of piecemeal, and it went pretty well, but you know, sometimes people left steps out or they sort of consolidated steps. So what would happen is the bromide would get hooked to the aluminum catalyst, like that. Okay, then the catalyst has a negative charge. And then you would use the catalyst. It doesn't, I'm going to use a chloride here. It doesn't really matter. It does matter, but the chloride's probably the stronger base. So then you'd use the catalyst, whoops, wrong place. I'm going forward again. You'd use the catalyst to take this carbon off, and then you'd snap these electrons in. And that's actually the reverse step to putting a carbon group on. Okay, and then you would get this. You'd have Al, Cl, Cl, Cl. Are you really getting in close to this? Mm-hmm. Pretty good. Mm-hmm. With the methyl hooked onto it, I did it the other way, so this is a chlorine. Bromine like that. Now when it's sitting like this, right, this makes the methyl kind of activated. So what does our aromatic look like right now? Our aromatic looks like this. This is exactly what we did in our little session. There's an H there, okay? So what you would do going forward is you would take the pi bond from the ring, attack the methyl group, kick it out, and you're just placing the methyl group in kind of like a non-kinetic location, in a location that's not stabilized by charge. So then what happens And you know, in class we drew nice mechanisms like this on the big board, or you guys did. What do you get from this? The methyl's now here. There's an H here. You know, and again, think about why this is not such a great, right, this is how you draw the Wayland intermediate, which is the charged intermediate. I'm not bothering to draw the resonance forms. All right, the reason this is not a very stable carbocation is that the delta plus is here, here, and here. And the secondary carbons don't support the delta plus as well as the alkyl groups do, or the tertiary sites. So when you, this is, right, these are ortho-para directors, but why is it doing this? As we said in class, because we had enough energy to do it, and because the system was actually equilibrating. It wasn't sitting static in its kinetic product state. So then once you get this, all you have to do is take the Al, Cl, Cl, Br, pull the hydrogen off, just like you're doing a normal Friedel-Crafts, but again, we're making all meta. And as you know, we spoke in lab about how this kind of compound could very well be the thermodynamic product because it has reduced steric interactions. Okay, so I hope that kind of refreshes you about what we did in lab, and I hope it made some sense. Of course, I will be in my office hours every day, 11 till 1, and for Saturday from 10 till 12, so there are a lot of office hours. And if you do need help with anything, please stop by. Okay, thank you. Bye.